Next up, we are going to look at the actual panel that we're trying to construct, okay? And I'm going to go through panel A right now. And to start off, I'm not going to worry about subdividing the numbers for right now. I just want to make sure my panel A works, and then I'm going to get my panel B to work, and then I'm going to deal with the actual splitting of the panels later, because that's kind of a design decision I'm going to deal with at a later time. So, what I have here is a list of 35 lofted panels, okay, and they're probably in a particular order. I'll worry about that later when it becomes necessary, but ultimately, I guess a smart thing to do would be to just turn off a lot of the excess information we have here. So some of our structural elements I'm going to turn off. These items over here, I can turn all this stuff off to make it sort of simplified. So let's look at it in this way for now. Now, the easy way to construct this, in my opinion, you may or may not have other ways of doing this, but I think it would be very, very easy to reparametrize a square into the top, left or right corner, right? See what we've got there? The black things are basically structural armatures. So if I can reparametrize a square profile into that corner, I can extrude it as an armature. And then I can grab one of the points on that armature and I can use that to extrude back to the panel corners, which is a different thing than probably the way some of you guys have approached it. So I'd like you to pay attention to this one rather closely. It's a good alternative. So right off the bat, I'm going to reparametrize this surface, which means I need to borrow this information back here. It's just kind of a good way for me to be pretty efficient. So loft into there. You're going to find that the loft is, looks like not only did it change directions, but it's not going to be correct here. So I'm going to bring my V minimum up toward the top of my panel. Actually, I'm going to leave my original loft on. So I'm going to bring it up toward the top of my panel. 10% is fine. And then I'm going to reduce the maximum down to about, you can make it square, it doesn't have to be square. Something kind of like that. Now it doesn't have to be perfect. This is kind of just a massing sort of exercise. Now, because these are reparametrized, they already have an orientation that's aligned to the panels themselves. So I could either pull my normals off of these surfaces, or I could pull my normals off of this surface. And if you still have your user-generated surface normal tool, you can use that. Basically like this, it just finds your surface normal directly off of it. Or you can do it off of the loft and do it manually. But for argument's sake, since not all of you saved your surface normal tool, I'm going to do it here. And again, the surface analysis tools you need, there are 3 of them. They're from Surface Analysis. It's Area, Surface Closest Point, and Evaluate Surface. So the surface is going to plug into Area. The surface is also going to plug into the surface input of Closest Point and the surface input of Evaluate Surface. But the UVP is going to be the connection into UV, and then the surface closest point is going to borrow the centroid as its point of reference right there. Okay, so these 3, they're kind of the golden trio of finding a surface normal. And this is what you're going to see here. You're going to see the panels are all located on each of the elements that we just crafted. And so we're going to have to extrude those elements. So I'll go to Surface Freeform Extrude. We're going to need the direction is going to need a direction and magnitude, so I'm going to use amplify under vector, vector, amplitude. And the vector, of course, is going to be the normal. That's this right here. The amplitude we're going to generate, but the geometry that we're going to extrude is this right here, our reparametrized surface. So let me drop a slider in here that says 0 to, I don't know, 5 feet, 5.00. All right, so this is going to be essentially the first step in generating this, but it's not the last. I'll do it sort of like that. Yeah, but it's definitely not the last. So I mentioned that the length needs to actually be built off of an attractor point, right? That's kind of the next level of specifics that you need built into this. So the attractor point well, let's first create a point to be our attractor point. So let me drop it down here sort of off of the surface a little bit, and then I'm going to rise it up. So let me just pull it up in the middle. Adam, I think this was the part that was confusing you, right? So that's going to essentially be kind of like my sun position, more or less. Not exactly the sun position, but it's more of like a, anyway, doesn't matter. We'll talk about that sun stuff later. But so basically, we're going to measure the distance of each of the centroids in this particular exercise. So that would be their base points, right? From this attractor point, and then we're going to use that as a modifier for the extrusion amount that there is for each of these items. Turn these off. Let's turn those off. Let's just look at these. And as such, I'm going to actually just kind of exaggerate these to 5 feet for all of them for now. Okay, so the actual attractor point function looks like this. We need to go up to point under vector. We're going to go to point, and we're going to use closest point, the singular one. So this is going to measure each and every individual point, its distance from the attractor point. So the attractor point will be referenced in and that's going to be our cloud of points. I know it's a little confusing because this is the multiple, but in the singular version we're plugging in.
That's the singular.
I know, yeah. This is the cloud as a list for cloud of points, plural. But then this one is the singular input of point, so it's a little backwards. But anyway, that's going to be your list of centroids. So that's these right here. And what it gives you is a numerical list of distances. So we can see this here like this. And in fact, this particular list should be flattened. Okay, so because I'm flattening this list, it means I want all of the elements in this exercise to read as a flattened list as well, wherever possible. So I'm going to go all the way back to the source, which are these, and I'm going to flatten all of them. You see that this entire section becomes flattened. That won't always be the case, but in this case, I want them to be flattened. And that's because I need to take this list of numbers and I need to remap them. You can't remap numbers unless they're a flattened list. Well, I shouldn't say it that way. You can only remap numbers that are in a particular set of a list. So when I change the range, it won't read each individual grafted list item only once and then, not be able to remap it. Does that make sense? Yeah? Okay. Well, anyway, I'm going to leave that there if you need to see it. So now my task is I need to take these numbers and I need to adjust it so that it reads per a particular range that I define. So that's under math domain and remap numbers. So now the value to remap is going to be the list of distance values. That's these. The source domain is going to be the domain, or the minimum maximum values of the list that you plugged in. So that's found using domain and bounds. We just take those numbers, and that creates a minimum of 25 and a maximum of 52. So I'll plug that in. And then a target domain. So this needs to be constructed as a domain, which means I need to go to domain and construct domain. And then I need to give it numerical values that are going to generate the domain minimum and maximum. So I'm going to do a minimum of 1 foot and a maximum of 5 feet. So now my remapped values are the same proportions, but minimum of 1, maximum of 5. So next step is, instead of the number slider amplitude, we have 35 values being plugged in for vectors, we have 35 values being plugged in for surfaces, and we have 35 numerical values that are going to be plugged in for our amplitude. And so you can see here, and I'll turn off even more stuff so it's more clear. You can see here what's happening is that the point value that's closest, go over there, is going to be the smallest, and then the point value that's farthest away is going to be the longest. Is that clear? Yeah? Okay. So there's one more follow-up item, and I'm only at 12 minutes on this video, so I'm going to, well, actually, I'll do it as a separate video. It'll make more sense that way.